Hi everyone, welcome to my lecture Community is Everything, which basically gives you a tease on how useful are graph analytics. A little bit about myself before we start. My name is Lior. I've been a data scientist for the past 6 years and in the past... A little bit about myself before we start. My name is Lior. I've been a data scientist for the last 6 years and in the past 3 years I'm also a team lead at Riskified. When I'm not working, I enjoy traveling, solving all kinds of puzzles, as you can see, and my favorite hobby for the past year has been Netflix binge watching. Hope I'm not alone here. So today we're talking about graph analytics, and in order to show you some of its cool features, I use a business need we had at Riskified. Riskified helps retailers deal with any kind of problem they face through the customer journey. Whether it's at account creation, login, checkout, or anywhere in the flow, we come to help. At some point in time, not so long ago, we started hearing merchants describe a new problem we call policy abuse. I'll explain policy abuse with an analogy we can all relate to. This is a wonderful time to be a private consumer. When you want to make a purchase, we have various vendors to choose from. We can decide where to shop based on location and brand reputation and price, shipping time, so on. So, great for us. For vendors, on the other hand, not so good. These vendors want to do everything they can, so we choose their shop. And they have a lot of competition going around now. What most of them do in order to attract us in is to offer many kinds of benefits for their customers. So what's the problem with that? It sounds fantastic for everyone. We get choices, the merchants give out benefits, but they get loyal customers in return. Where's the catch? So here are a few examples. One of the benefits merchants offer in order to attract new customers is a discount on their first order. Notice how they say here, new customers only, and that codes will be sent to your email address. Well, I have to wonder whether a new email address really equals a new customer. I mean, we all know a new email can be generated in a matter of minutes, so we all understand the secret here. Most people are legitimate shoppers. They use the discount once. But some people think, why don't I just use this 20% off all of my purchases? And they go ahead and create new emails with fake details and new accounts and get their discount codes over and over again. Another really popular example is referral programs. We all know how it works. You refer your friends, they get something, you get something. Everyone's happy. Unless instead of referring your friends, you refer your fake accounts and accumulate the net credit over and over and over again. One last example is the most sophisticated use case we've seen so far, and that is when a sneaker merchant has a limited quantity of popular pairs of shoes, and they offer their loyal customers a chance to each get one pair. In many cases we've seen, bots who generate new accounts can end what is supposed to be a 24-hour celebration in a matter of minutes. So I hope the problem is clear by now. We have an order, and we need to figure out who's behind that event, and if we've ever seen them before. The question we ask is, are they really new to us? Let's see what do we have to work with. The first piece of the puzzle is data elements. Every order we collect has many elements as data points. For example, if I place an order and I try to use a promo code, I enter my email address, my billing, shipping details, phone, credit card, and so on. On top of that, Riskified collects additional data, and these combined are the elements we can work with. So, as I just mentioned, elements are data points of orders. On top of orders, there are accounts. An account can have 0 to n orders, and each order can have different data elements. These elements are what we're going to refer to later on as edges. The accounts are what we'll refer to as nodes. Let's talk about some relevant graph terms. Graphs are essentially networks of a partially or fully connected objects. You can think of a social network as an example. The objects are people, like you and I, and the definition of connection between us is whether we are Facebook friends, we follow each other on Twitter, Instagram, and so on. Nodes in a graph are the objects, you and I. An edge is what defines a connection between those objects or nodes. If we stick with our previous example, an edge will be drawn between you and I if we are Facebook friends. A component in graph theory is a subset of a graph in which any two nodes are connected to each other by edges. In our example, we can see we have one component connecting nodes A, B, and D. Node C is also a component of size 1. It only has one member, and that is node C. To emphasize, if we were to break this connection between nodes A and B, we would end up with 3 components. Now that we all know these graph terms, I'm sure you ask yourself, well, what can I do with these? Here are a few examples of analyses we can perform on graphs. The first type is path analysis, which is the examination of relationships between nodes in a graph. In other words, it determines the distance between pair of nodes. So this is a measure of proximity in a network. We can also use connectivity. The connectivity of a graph is an important measure of its resilience as a network. It asks for the minimum number of elements, either nodes or edges, that need to be removed to separate the network into isolated subgraphs. You can think of a network describing a virus spread and how crucial is connectivity in that case, right? We want to stop a spread, we need to understand exactly which ties to break in order to make that happen. Last, at least for today, we have centrality. Centrality analysis enables us to estimate how important a node is for the connectivity of a network. For example, it can be used to determine the most influential people in a social network or find the most accessed web pages. Let's turn back to our data and remind ourselves how it looks like. So this is what we have in a tabular form. That's the essence of how transactions look like. I've obviously left a lot of details out, but this gives you enough of a view to work with. Now let's take everything we've learned and put this all in a graph. And this is how it looks like when modeled into a graph. Now we're quickly able to make some assertions about our data. We can see how connected or isolated are our nodes using the edges we've just defined. We can calculate the shortest path from one node to another and extract which nodes are centralized, and actually, this looks much more informative than the tabular view we've just seen. And after all, why is this still not enough? In large graphs, especially those who are around textual elements in the context of multiple data points, there's a tendency for many nodes to become connected and create giant components. In order to separate these densely connected networks into smaller, cohesive entities, it makes sense to use community detection to help. When analyzing graph networks, it could be important to discover communities inside them. If you think of a social network, for example, it could be helpful to find people with similar interests and keep them tightly connected, so we can show them the same ads, suggest the same groups, events, and so on. In general, community detection algorithms can be used to detect groups with similar properties. If that rings a bell and reminds you the problem I initially introduced, you got it. This is exactly what we want to use in order to find groups with similar attributes and classify them as the same entity. And then we can say, hey buddy, seems like you've used this promo code before. Sadly, we cannot allow you to redeem it once more. So now, one of the components we had before is split to 2. Community algorithms basically split nodes into groups of size 1 to n. How does the split happen? Well, there are multiple algorithms and each has its own metric to help decide on a node's group. In the essence of time, I'll briefly explain the logic behind the most popular optimization measure called modularity. Modularity is a scale value between minus 0.5 and 1 that measures the relative density of edges inside communities with respect to edges outside communities. In simple words, if we optimize for modularity, the communities we generate will indicate which nodes are more densely connected between each other than to the rest of the network. Optimizing this value theoretically results in the best possible grouping of nodes in a given network. Now, I found a cool example taken from a Git repository called Communities that show this in action. So, we start with every node in its own group, and we see there are edges between many nodes to others. Now, a heuristic algorithm groups nodes together until it finds the optimal group for each, and at that point, modularity is the closest it can be to 1. So when we at Riskified see accounts popping up in our system, we try to match them to their relevant community. They are no longer separate entities, but a tightly connected groups of nodes which we can now apply all kinds of machine learning techniques on. To conclude, we had a business need, solving the problem of customers abusing benefits offered by the merchant while disguising as new customers. We used the strength of graphs to help us solve this problem and identify hidden similarities between seemingly unrelated accounts. And this is just one example of how graphs are useful. If I had to offer you one thing following this talk, it would be that you look for a problem within your day-to-day task that fits this type of modeling, and go ahead and explore it yourself. I hope I helped you figure out it's more intuitive than you imagine. Thank you for your time. For any comments or questions, feel free to reach out over social media.